Thank you all for being here. This is joint work with my advisor, Anant Sahai from Berkeley. And today I'm going to talk about a situation in Stackelberg leader-follower games in which the leader commitment may not be fully revealed to the follower. And we'll study implications of what this could mean for both players of the game. So many of you have probably seen Stackelberg games in some form or another. But just to get everybody on the same page, I'd like to start off with an example that's commonly used in the security games literature and an example that I think motivates the power of commitment really well. So let's think about a situation where a defender wants to protect her two targets from some form of attack. And she has only one guard that she can use for this protection. So her pure protection strategies would involve her sending her guard to either target 1 or target 2. And this is a situation in which the defender actually cares a lot more about defending one target over the other. So she cares a lot more about target 1 than target 2. So this is her utility function. The defender is then faced with an attacker who importantly does not know the defender's utility function. And the attacker has a utility function of his own, which is that he simply wants to attack the target which is less likely to be defended by a guard. And in this situation, the way you can think of the power of commitment is that what the defender can do is she can actually commit to a protection strategy that makes the attacker aware that she is more likely to be defending target 1 than target 2. And thus, the defender can incentivize the attacker to attack the less valuable target, that is target 2. So this is the intuition for the power of commitment and how the defender can use this power of commitment to her advantage. More generally, this is an example of a Stackelberg leader-follower game. This has been studied for a while in the context of security games, and recently it's also being used very much in Bayesian persuasion. In this game, the leader can more generally reveal a mixed strategy commitment, which is simply a mixture between M pure strategies. And the follower has P pure strategies, let's say. So based on this, we can define a payoff matrix for the leader. So again, as before, this is the payoff matrix that's not known to the follower who's playing the game. Once the leader reveals this commitment, we assume that the follower is exactly able to observe this commitment and best respond accordingly. So the best response happens according to a follower payoff matrix. And here I'm just showing you a schematic of how the follower might best respond as a function of the mixed strategy commitment. So we can actually divide it into different best response regions. If you look at the schematic alongside the security game I've just talked about, the way you can think about it is that if the defender were more likely to protect target 1 than target 2, the attacker would respond by attacking target 2, which is simply the blue region in that schematic that I'm showing you. And throughout the game, you can think of this as the response that the defender will really want. On the other hand, if the defender were more likely to defend target 2 than target 1, the attacker would simply attack target 1, which is a situation that the defender really does not want. So algorithmic game theorists have studied this Stackelberg leader-follower game in normal form. And in fact, you can characterize the leader payoff function, as it turns out, as a piecewise linear program over each of these different best response regions. And it's in fact possible to exactly compute the optimal Stackelberg commitment as well as the Stackelberg payoff. So let's look at what this optimal commitment is in the context of this simple example. So we already intuitively saw that the defender would intuitively want to convince the attacker that she's more likely to be defending her more valued target. And thus the attacker would be incentivized to attack target 2. But the defender can do even better than that by in fact choosing a mixed commitment. What she can do is she can choose her protection strategy so that she's just a little bit more likely to be defending target 1 than target 2. But at the same time, she can also ensure that there's some probability, of course this is less than half, that she'll also be able to defend target 2, and thus neither of her targets would be compromised. So the intuition is that the Stackelberg commitment is actually obtained by doing this and then tending epsilon in this strategy towards 0. So formally in this game, the definition of the optimal mixed Stackelberg commitment in fact involves a defender defending target 1 and target 2 with equal probability. So there's an important caveat in this definition, which is, in fact, theoretically speaking, when the defender does this equally likely to protect strategy, the attacker is actually ambivalent between attacking target 1 and target 2. And the assumption that's commonly made in the Stackelberg games literature is that in this situation, the follower in fact breaks ties in favor of the leader. So this is an assumption that's been made in algorithmic game theory, where we compute the Stackelberg commitment, and also in prior economics literature. And the reason the assumption is made is to actually show that there in fact exists an optimal commitment. But it's an assumption that I find very interesting, and it also already hints at some kind of possible instability in this solution concept. So there's a very important assumption that goes into the solution concept, which is that in fact this commitment can be fully revealed. So there are two important aspects to this. First of all, the follower needs to be able to exactly observe the leader commitment. And second of all, the follower needs to believe that the leader is in fact committing to something. If you think about my security game, and if I'm the defender, it's not that I can simply say out loud that I am going to be protecting one resource more likely than the other. There's no reason a priori for the attacker to just believe me. I need to actually establish this commitment in a credible manner. So in the context of a security game, a reasonable model for doing this is through a number of finite deployments of the commitment. So in the security game, what the defender will be doing is she will actually, in every deployment, she will choose a realization of her mixed commitment and either end up defending target 1 or target 2. When the attacker sees this, he will best respond by simply by attacking the target that was protected in a fewer number of deployments. So we can ask all the questions in the setting as before. Remember, this is still a one-shot game. But now what we're doing is the defender is just revealing her commitment instead of exactly. She's revealing it through a finite number of deployments. And now we can ask all the questions we asked before. We can ask whether the defender still enjoys a mixed power of commitment like she did before. So this is an example of what I'm going to call the partial commitment game in this talk, where instead of the leader revealing the true commitment, she's going to be revealing an IID deployments. I'm making this assumption for now, and this is a good assumption in the context of security games. I'll talk about a repeated game formulation later in this talk. For now, we're going to assume this, and when both leader and follower know that the leader is going to be displaying her commitment through IID realizations, the follower can form some sort of maximum likelihood estimate of what the commitment is going to be. And instead of responding to the true commitment, he will be responding to this maximum likelihood estimate. So let's go back to our schematic of the best response regions and think about what this really means. Originally, we had a true commitment. We assumed the follower could fully see this, and we knew exactly where the best response would lie. And things were simpler in a way. Now what happens is when we reveal a commitment, there's some potential uncertainty. So there's actually a number of different ways the commitment could be perceived because these realizations are in fact stochastic. And thus the identity of the follower's best response is stochastic as well. It could in fact be different from what was intended. So what this really means in the context of the optimization problem is we now have a robust payoff that the leader should expect. And now this no longer enjoys any simple linear or even convex structure. This turns out to be a non-convex optimization problem. And in fact, prior work has shown that this is computationally intractable to compute the exact optimum payoff. Prior work has also looked at convex relaxations and empirically studied this. Today, we'll be looking more at some analytical questions that naturally arise. So I'll be asking whether the Stackelberg commitment is still a good idea. I'll be kind of delving into the question of what we want to do to ensure that the follower is able to exactly learn our commitment because there's now uncertainty in how the commitment is being perceived. And finally, I'll ask the question about whether the leader even wants her commitment to be learned in such a situation where there's uncertainty, because as we know, this is a non-cooperative setting and the incentives of the leader and follower need not necessarily be aligned. So we do have good answers to these questions for the special case of a zero-sum game where it actually turns out that just choosing the Stackelberg commitment is in fact approximately optimal. Let's see what happens for a non-zero-sum game. So the first thing I want to tell you is that the Stackelberg commitment is frequently very unstable. I'll now show you just how often and just to what extent this is actually the case. So the real problem with the Stackelberg commitment in a non-zero-sum game is the fact that it's really lying on a boundary between these two best response regions. So if you think back to the security game, the optimal commitment was me, in fact, choosing uniformly at random between defending both my targets. And what this means is that even if there's a slight chance of this commitment being misperceived, I could elicit a very different response than what I expected. So for example, if I were doing this, and in my deployments, if it turned out that it looked like I was more likely to defend target 2 than target 1, the attacker would attack target 1, which is my more valued target. This is a situation I really, really don't want. And looking at this diagram and looking at the typical realizations of where my commitment is being perceived, you can see that this is actually a very likely event. This is not an event that's very improbable or very low probability. You may think this is not surprising that this is happening for, say, a small number of deployments where there's bound to be a lot of uncertainty. What's maybe a little more surprising is that this happens even when the amount of uncertainty in how the commitment is perceived is going down. So even if we had 10,000 deployments or even 1 million deployments, this would still be an issue. And it's because the Stackelberg commitment is in fact exactly in the boundary between two best response regions. So now we can also ask the question of whether this is a problem only with this toy example that I showed you. It turns out that this is a problem more generally for non-zero-sum games. So here we simulated the average difference between the ideal Stackelberg payoff and the actual Stackelberg payoff that was being manifested. As we increased on the x-axis, I have the number of observations. And you can see that there's a systemic gap. And this is a gap that's not, in fact, decreasing as the amount of uncertainty goes down. Formally, what we were able to show is that this is, in fact, the suboptimality is a problem for any non-zero-sum game where the optimal Stackelberg commitment is, in fact, mixed. So this is an if and only if statement. If the game is zero-sum, as we saw before, this is not an issue. And if the Stackelberg commitment were pure, there's, of course, no issues that arise due to observational uncertainty. So we saw that the problem with the commitment was really that it was on the boundary between two responses, and that was what was making it really unstable. And the key idea we used to actually make our commitments robust to uncertainty was to deviate from the boundary. And what we want to do is we want to do this in such a way that we are, in fact, preserving our follower response. Intuitively thinking about the security game, what you would do is instead of protecting target 1 and target 2 equally likely, you would protect target 1 a reasonable amount more often and ensure that even if there were fluctuations, it still appeared to the attacker that this was, in fact, the case. So that's not all that we want to do. We also want to make sure we're still leveraging some power of mixed commitment, and we don't want to move too far away from the boundary at the same time. So what actually ends up happening is what we did with our robust commitments is we actually optimized a trade-off between preserving the identity of the follower response with the fluctuations in how the commitment was being perceived, and still making sure that we were sufficiently close to the optimal commitment so that we could preserve some of our mixed commitment power. And we were able to actually analytically construct these commitments and show that we could approach the ideal Stackelberg payoff as the amount of uncertainty went down. So here in my simulation, I'm actually showing you how the expected leader payoff varies as the number of observations again. We saw that the Stackelberg commitment is a bad idea with even a little bit of uncertainty. Now I'm showing you that our robust constructions, in fact, approach the ideal Stackelberg payoff as we increase the number of observations. And we showed this more generally. We actually have a specific rate of convergence here, which goes in terms of the number of observations as 1 over square root. And we also have a factor which is the number of pure strategies for the leader, and that's important because we need to make sure that the commitment can somewhat be learned by the follower in this situation. So there's something I've swept under the rug here in all of this discussion, which is that we kind of assumed that these different than expected follower responses are always bad for the leader. And while that was true for this example, this is not always true. If you think about a zero-sum game, a different than expected response for the leader would actually be a better than a worst-case response. And there are situations where maybe the leader could gain by purposely trying to elicit a mismatched response. So now we ask whether that is in fact the case. And going back to the robust optimization problem, is that optimum value itself much greater than the ideal Stackelberg payoff? It turns out this is not the case, and we can show that maybe we can gain a little bit over this ideal payoff, but not by too much. For example, and I'm not going to go into too much detail here, but if you chose any commitment, the idea is that by eliciting different responses, you would either think about responses that are very, very far, that would require a commitment to be perceived very, very differently, which is a very low probability event, or you would expect responses that are close to expected, but turn out to only have a very incremental gain in payoff. And what this really means is we have an upper bound on our robust optimum payoff. Remember, this is actually computationally intractable, but we showed that in fact you cannot gain too much over the ideal Stackelberg payoff in this situation. What this means as a consequence is that our robust commitments are in fact approximately optimum. And you can actually see this in this. And this is just one simulation in the random ensemble. Remember, we can't exactly compute this optimum feasibly for a number of different examples. So here I'm really saying that the leader is approximately incentivized to make our commitment learnable, even though it's a non-cooperative setting and there's uncertainty. It's important to remember I'm saying this in the context of in a way, a specific model for this conclusion, which is that there's this independent, identically distributed commitment deployment. This is a good model for a security game, but for some of the other examples where this can come up, it's maybe more realistic to think about a repeated game model where both the leader and the follower have a lot more freedom in how they could play. So I'm going to just give you a very small snapshot of ongoing work I'm doing in that area. So there's been a nice historical connection between the Stackelberg solution concept and reputation building in many economic scenarios. What this involves is a repeated game between a leader who has some private information and several different followers. And the leader is incentivized to build up some sort of reputation in the situation. This has been studied asymptotically. I'm now interested in the finitely repeated setting. And in particular, I want to ask if there's some real incentive for the leader to deviate from the kinds of protocols I've discussed, which is really playing in a mixed way and needing to be robust to the ensuing uncertainty. For example, the leader might try to accelerate the follower's learning process by playing in a deterministic way to imitate what looks like a random process. It turns out that in these situations, the leader's play would become sequentially predictable, and the followers could really exploit this, and this is actually not a situation that we want. On the other hand, the leader could try and mislead the follower on purpose, and this is also a situation that it turns out if the follower were kind of calibrated to this uncertainty, we can formally show that the leader would not gain too much over ideal Stackelberg in this situation either. So the main takeaway is that even in a repeated setting, the credibility and commitment does need to be built up through this randomization, and I'm still trying to answer the question of precisely how much of this is needed in this particular setting. So a lot of questions that come up at the intersection of learning and games in this finitely repeated setting, a lot of things to be working on. So what do you want to take away from this talk? If you're using a mixed Stackelberg commitment in a real-world deployment, so we've talked about security games, this is also likely to be an issue in many persuasion mechanisms, you need to be careful because you need to think about exactly how this is being displayed, and there's a good chance that it could be unstable in the real world. We showed that, in fact, getting these robust commitments is something we can compute in polynomial time, so we can, in fact, exactly compute these. I didn't talk too much about the technical details in high dimensions, but we could use the fact that our best response regions were convex and polytopes, and we used a number of connections to interior point geometry to explicitly construct our commitment constructions. And finally, we showed that the leader is approximately incentivized to, in fact, convey her commitment and make it learnable in a situation where there may be uncertainty, even though the setting is non-cooperative. So I'm really interested for the future to think about where these ideas could be useful more broadly. So I'm interested in thinking about multiple leaders where there could be some kind of competition. I'm also interested in what this could mean for mechanism design more broadly, where you have multiple so-called followers. And finally, I think it would be really interesting to integrate these ideas with the rich literature in which leaders are, in fact, learning about followers themselves. So there'd be learning on both sides of the equation there. So that's it from me. Thank you for listening. Yeah. Mm-hmm. So what exactly was what was the conclusion?
So to me it sounds very similar, right? So they also think about this robustness issue that the follower might have limited observation, or might be a little off, or do something a little bit suboptimal, and they look into how to generate this program or something that
Yeah, I'm aware of this work. I'm aware of this work. I think I'd seen the year a little bit later. So there are many different models for uncertainty. And that model is actually different in the sense that it's not a stochastic deviation in how the commitment is being observed, because what they're doing is they're saying that there's some probability that the follower sees the true commitment, and there's another probability that the follower actually anchors on some uniform distribution. So I remember there was actually more recent work I remember from Millen's group that talked that, so that was what I kind of referenced earlier, where they look at the limited observation. Okay, I guess the one I'm thinking about is one from 2012, 13. It was by their group as well, but we can talk offline. We can talk.